show, you're going to learn how to count. Couple words you should be aware of. Permutation means I'm going to have an arrangement of things, and the order in which I place those things matters. First, second, third, fourth, that matters. Combination means I'm going to have arrangements of things or collections of things, but they're unordered. So if I mix the same set around, that doesn't actually constitute a new set. It doesn't matter what gets placed to the left or the right, etc. Repetition, you already know what it means. Same thing happening 2 or more times, okay? In this context, repetition is either going to be allowed or not be allowed. All right? We're either going to be allowed to take the same choice twice or not. And then lastly, the fundamental counting principle. If there are a certain number of ways to do one thing, different number of ways to do another thing, and I want to find out how many distinct possible ways there are to do both things, I'm going to multiply. All right, let's see how that works. Fundamental counting principle is actually the easiest piece to wrap your mind around. Classic example, we talk about clothes. You got 3 pairs of pants, 5 shirts. How many different outfits can you generate? If I drop those in place, you can see that I'm almost even making a multiplication table like what's in the back of a composition book, right? And you can see if I fill out this chart, 1 shirt going with 1 pair of pants, we got 5 different possibilities with each pair of pants. Right? So 5 times 3, 15 possible outfits we can generate from those 5 shirts times 3 pairs of pants. Check this out. 5 chairs, 3 people, how many different ways to arrange them? You're going to think, at first glance, this is the same problem as before. 5 times 3, 15, done, good. You're going to be wrong. All right? One of the toughest things when we're dealing with counting is interpreting the situation, and the situation of arranging people into chairs is completely different from the situation of choosing outfits. When we were choosing outfits, we wanted to take 1 shirt and 1 pair of pants. When we're arranging people in chairs, it's not that we're taking 1 chair and 1 person. All right, I can move 2 of these guys around and leave 1 of them steady like this. All right, move, move, move. That first guy sat in that first chair through a few different arrangements of people, okay? So it's not as simple as just saying 5 times 3, because choosing 1 person in 1 chair itself has multiple options associated with it. All right, so let's go back to the beginning with this problem. Start with an empty room. Let 1 person come in. All right, that person's going to sit down. How many options does that person have? How many ways can that person sit down? 5 ways, right? They have 5 chairs open to them. Second person comes in. First person is seated. How many ways are left for the second person to sit, right? No matter where the first person sits, second person is only going to have 4 options left to him. Third person comes in. Same deal. After the first 2 people are seated, how many options does he have left? He's got 3 options, right? No matter where the first 2 people sit, he's only going to have 3 options left to him. So to recap, first person, 5 ways to sit. Second person, 4 ways to sit. Fundamental counting principle says if we're just going to seat 2 people, 5 times 4, 20 different arrangements. Now you can see those 20 different arrangements there. Third person comes in. He's got 3 different ways to sit. How many different arrangements are there? How many different permutations are there for seating 3 people? 5 times 4 times 3, 60 different arrangements. Let's look at the same situation but switch something up. Suppose we don't care who is in what seat. We just care which seats are filled, which seats aren't filled. In other words, this situation with 3 people sitting in the first 3 seats is considered the same as this situation, and this one, and this one, and this one, and this one. Okay? Lots of different ways that you could seat 3 people in the first 3 seats, but we don't really care who's where. We just care first 3 seats are filled, and so on. In that context, got 5 chairs. How many different ways can we arrange 3 people? Now we're going to start with our answer from the last situation. 5 times 4 times 3. There are 60 different ordered arrangements or 60 different permutations of people. We're going to want to divide from that how many times a combination gets repeated. Okay? How many different ways can 3 people get rearranged within just 3 seats? That's going to look like this. First person, 3 choices. Second person, 2 choices. Third person, 1 choice, or total of 6 ways. And I showed you those 6 ways for the first 3 seats. 6 ways that 3 people can get arranged into 3 seats. Final answer is going to look like this. 60 divided by 6. There are only 10 combinations that we can have of filled and empty chairs in the situation of 5 chairs, 3 people. Since 10 is such a small number, I decided to prove it to you, show you how exactly that looks. Here's our situations. All right, there's 4 ways to have 2 empty chairs next to each other, 3 ways to have 2 empty chairs spaced apart by 1, 2 ways to have 2 chairs between the empty chairs, and 1 way to have the empty chairs on the ends, right? 10 different combinations. In general, if you want to calculate a combination, an unordered arrangement, you're going to want to calculate the permutations for that situation first, and then you're going to divide by another permutation, a permutation of a smaller set. So like, for example, ours was combinations, 5 chairs, 3 people. First, we take permutations of 5 chairs and 3 people. Divide that by permutations of 3 chairs, 3 people. Example 3 looks similar to the ones we've already seen, but yet again, slight difference in the kind of situation. How many different ways can we split 5 coins among 3 people? All right, and I say unfairly because the first guy could get all 5, or he could get none of them, or he could get 3 of them. All right, so this is how to look at this situation. First coin, it's got 3 different people that it could go to, right? So 3 ways to give out the first coin. Second coin, still 3 different ways to give it out, right? So there's 9 different ways that I could give out those first 2 coins. Third coin, I could still give it 3 different people that I could give it to. Same thing with the fourth coin. Same thing with the fifth coin. All right, so we've actually got 3 times 3 times 3 times 3 times 3, or 3 to the 5th power, as the number of different ways that we could give out coins. Now that's if the order that we're giving the coins out matters. What if there's not an order? What if I don't care who gets the first and who gets the third? I only care for totals. In other words, what if all of these situations are the same? First guy ending up with 3 coins, second guy ending up with 2 coins, third guy ending up with no coins. All of those situations are the same. Now, combinations where repetition is allowed is the toughest one to wrap your mind around. Me, myself, I might choose, instead of using the fundamental counting principle in a situation like this, to just make an organized list. First guy, 5 coins. Other 2 guys, no coins. That's one combination. All right, there's one way for the first guy to have 5 coins. 2 ways for him to have 4 coins, right? Give that 5th coin to the second guy or to the third guy. 2 different ways for him to have 4 coins. It's 3 ways for him to have 3 coins. All right, I could give 2 to the second guy, 2 to the third guy, or split that between them. 4 ways for him to have 2 coins. 5 ways for him to have 1 coin. And there's 6 ways for him to have no coins. All right, this is an organized list of all of the possible outcomes of the situation when repetition is allowed and order doesn't matter. I could count up all those possibilities. Now it does need to be an organized list, so I make sure that I didn't miss one of the possibilities, but I could count them up. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21. 21 possible ways to split 5 coins between 3 people if order doesn't matter. How would I do this without an organized list? How would I do this mathematically? Like I said, this is going to be a brainful. Okay? If you notice in this list, the third guy is fully determined after we decide what to do with the first 2 guys. So for example, if you look at just when I said second line, first guy has 4 coins, second guy has 1 coin, there's nothing left for the third guy. Or if the first guy has 4 coins, second guy has 0 coins, that last coin has to go to the third guy. So the third guy doesn't really get a choice, we will say. All right, so I'm going to set the situation up like this. 2 triangles, 5 circles. All right, and I will move those triangles to positions to indicate how many coins each person has. All right, so this formulation would indicate 1 coin, drop down to the first guy, 2 coins, drop down to the second guy, and that leaves 3 coins left, or that leaves 2 coins left for the third guy. All right, switch that up just so that you can see how this looks. 2 coins, drop down to the first guy, 1 coin, second guy, third guy, 2 coins left. First guy 4 coins, nothing for the second guy, third guy gets that 1 coin. All right, so that's how this system of pictures is working. All right, and now I have 5 circles, 2 triangles, and I can ask a new question. How many different ways can I arrange those 7 things? That'll be permutations, and I'm going to need to divide out my repeats. So how many different ways can I arrange 2 triangles? And I'm going to have to divide out my circle repeats also. That's going to look like this. 7 ways to place the first thing times 6 ways to place the second thing times 5 ways to place the third thing, and so on. Divided by, and you can see it right there. Okay? Do all that math, you can double check it. You're going to come out with that number 21, which is the same thing we had when we did an ordered arrangement. You can decide for a situation like this, is it going to be easier for you to make a organized list, or did you follow that whole thought process? Okay, truth be told, you can make organized lists for all of these situations if you're struggling to think about the mathematics. The problem is, if we jump back to that 88 key example, it's going to be a really long list if you deal with big numbers. Right? And that's where the mathematical formulas come in handy.